Hi, I am Shekhar, a M.Tech first year student at Department of Electrical Engineering IIT Tirupati. As a part of Communication Networks course, I am here to present a paper titled Elastic Multi-Resource Network Slicing Can Protection Lead to Improved Performance? Presenting you the details of this paper. This paper was published on 22nd January 2019 under the subject Networking and Internet Architecture by Saxiozene Gustavo de Veciana at Department of Electrical and Computer Engineering, the University of Texas, Austin. Now introducing the work done in this paper. Our future applications are data intensive and hence next generation networks face the challenge of supporting these applications like self-driving cars, mobile data analytics, augmented reality AR, virtual reality VR, Internet of Things IoT, etc. And service providers also share common storage, computation or connectivity at network edge. The problem of allocating resources at the network edge is solved by Share Constraint Slicing SCS as proposed in this paper. This SCS provides interslice protection, improved job delay, and improved throughput. When the cost of implementing SCS is excessive, especially in case of dynamic mobile users, weighted max-min as a surrogate resource allocation can be used in the case of SCS in resource allocation. Now defining some of the terms used in this paper. The set of slices is denoted by capital V and the set of resources by capital R. Each resource is considered to be normalized with capacity 1. The set of user classes in a slice is denoted by C superscript V and the total user classes C is denoted by union of all classes of each slice. And the set of users of each class is denoted by U subscript C. Users on slice V is denoted by union of all the users of each class per slice. And overall set of users is denoted by union over all the users of each slice. And similarly, if we have heterogeneous resources, the resource demand vector of user class C is denoted by D subscript C, that is, it contains a vector of the fraction amount of each resource required per user class denoted by D subscript C superscript R, where D subscript C superscript R is the fraction amount of resource R required by the user of particular class C. And the processing rate of a user U is denoted by lambda subscript U. Number of active users in a class C at time t is denoted by a random variable n subscript C of t, and on slice is denoted by n subscript v of t, and this n subscript v of t, that is number of users in a slice, is obtained by summation of all users per class in a slice. And these realizations are denoted by small letters, and the user classes using resource R is denoted by C subscript R. Now consider an example for better understanding. Let us have three vehicles, each belong to distinct user class, and two regions, region 1 and region 2, and two slices 1 and 2. Here user 1 and 2 belong to slice 1 and user 3 belong to slice 2. User 1 is performing only data transmission and user 2 and 3 are performing data analytics. And we have five resources, that is 1 backhaul, 2 connectivity of region 1, 3 computation of region 1, 4 connectivity of region 2, and 5 computation of region 2. Since user 1 is performing only data transmission, the resource demand vector of this user 1 is denoted by 1 comma 1 comma 0 comma 0 comma 0, and user 2 and 3 are performing data analytics. Their particular resource demand vectors are 0.6 comma 0 comma 0 comma 1 comma 1. For example, 0.6 of this user 2 and 3 represent they demand almost 60% of backhaul to perform better in data analytics. After applying share constraint slicing as proposed in this paper, the rates obtained for these users are user 1 get 0.4, user 2 get 0.5, and user 3 get 0.5 as specified in the table. Now presenting you some of the definitions. First one, share constraint weight allocation, that is SCWA. As we allocate weight for each user, that is WU, it is considered as share constraint weight allocation. If for each slice, if we submit over all the users of each slice weights, we get the total capacity of the slice as allocated even before the weights are allocated to the user. And the weight of each class is denoted by QC, which is the sum of all the user weights of particular class. And two examples here are equal intra-class weight allocation, where user weights are same within the user class, and equal intra-slice weight allocation, where user weights are same within the slice. And the second one is alpha share constraint slicing, alpha SCS. As we consider intra-class weight allocation with some class weights Q and class allocation rates phi, alpha SCS corresponds to maximizing a function of phi and Q, where the capacity of each resource is at most 1, and hence this is imposed as a constraint in this maximization, and alpha is greater than 0, a predefined parameter. Continuing the definitions from previous slide, the utility functions in the previous slide maximization can be observed here for two cases, that is alpha equal to 1 and alpha greater than 0, and the utility function for each slice is also specified here. Coming to the third one, class level alpha fairness. Under equal intra-class weight allocation given class weights Q and class level rate allocation phi, it corresponds to alpha fairness if it is solution to maximization of utility function of slice V for alpha equal to 1 and alpha greater than 0 as specified here. Now, representing the static analysis of this paper, where users are constant for each slice, system can be modeled as a solution to the problem of maximization of rates of summation of all utility functions of each slice with rate phi and weight q, with imposed constraint of each resource has capacity of at most 1. Discussing some of the desirable properties here, like first one, protection, that is interslice protection, defined as no slice is penalized under this share constant slicing, that is SCS sharing. To characterize this protection among all slices, we discuss how the performance degrades is possible for each slice by switching from static partitioning to alpha SCS sharing. This static partition has its slices decoupled, and hence interslice protection is achieved possibly in this static partitioning, represented by a theorem for a given weights Q. When the resource allocation is performed by alpha SCS, difference in slice utility compared to static partition is upper bounded by an equation represented here with inequality less than or equal to, that is difference between utilities of static partitioning and alpha SCS for alpha not equal to 1 and alpha equal to 1. Discussing the right hand side terms, the first one can be viewed as the average of 1 minus 1 by alpha order movement of charged resource usage of slice V's user, where the second term is of the overall users. For 0 less than alpha less than 1, sharing tends to benefit slices with greater average user usages, that is at the cost of other slices. For alpha greater than 1, slices with small average user prices are almost preferred. Considering the next desirable property of static analysis, that is envy freeness, defined as no slice is motivated to swap its resource allocation with another slice of smaller share. Consider a slice V and slice V dash considered for swapping. Before swapping, we have phi superscript V comma S as a rate allocation for slice V, and after swapping, the rate allocation is a solution to the problem as specified here with imposed constraint of capacity of resource or at most to the fraction of resource provision to slice V dash. A theorem is defined here as the difference between utility obtained by slice V under alpha SCS and that under static partitioning within the resource provision to another slice V dash is upper bounded by the inequality as specified here. As a special case, when we consider alpha equal to 1, the right side of this inequality becomes SV dash minus SV, which is the capacity of particular slices, and thus slice has no motive to swap its allocation with another that is less or equal share, which implies that SES is envy free. Now considering elastic traffic model, where system model can be defined as each user carries a certain amount of work and leaves it once it is finished in the system, and assumptions made here are as follows. For a class C user, service requirement follow an exponential distribution with mean 1 by mu c, and arrivals follow Poisson process with intensity Vc, and hence the traffic intensity of user class C is defined as rho c equal to Vc by mu c, and also here intra slice weight allocation is assumed, and alpha SCS criteria is obtained by maximizing a utility function as specified here with imposed constraint of each resource has utmost capacity 1, and the stability in this dynamic network can be assumed to be satisfied, that is the network is assumed to be stable or obtained to be stable if it satisfied the condition, that is summation over all the classes using resource R with traffic intensity rho c into d demand vector dcr of a particular resource, which is less than 1. This is the condition to be satisfied for the network to be stable. This must be satisfied for all the resources. Now, discussing the simulation results as specified in this paper, the performance of SES is compared with benchmarks like dominant resource fairness DRF and discriminatory processor sharing DPS. The performance trade-offs are delay and throughput, where delay is defined as the sojourn time of each user, that is, time taken for a user to complete service, and throughput is defined as workload divided by the sojourn time of each user. The performance trade-offs of single resource case is specified under symmetric traffic here. That is, we have two slices and each slice have one user and one resource with utmost capacity 1. For a symmetric traffic, the trade-offs are plotted here by simulation, where blue one represent the SCS as proposed in this paper and red one represent DPS. It can be clearly observed from this figure for a symmetric traffic, that is we have equal mean arrival rates and mean workloads. The throughput on an average for SES outperforms DPS. Now, extending the discussion on simulation results, the performance trade-offs of single resource case under asymmetric traffic, that is different mean arrival rates of users. The throughput trade-off and delay trade-off can be observed here in the graphs. Uh, the mean throughput of SCS is better than DPS as observed here, and similarly in delay also SCS is marginally better than DPS. Similarly, busy period of slice 1 and 2 versus load intensity is also observed here. That is the fraction of periods the slice 1 and or 2 or both are busy with the traffic intensity is plotted here. One can observe that for both SCS and DPS, the time fraction when both these slices are busy increases with traffic intensity rho, and that only one slice is busy first increases with rho, and then it decreases when rho is high. First it increases due to underutilization and then decreases when rho is high. Now testing the performance of the proposed SCS in complex setting. An example is considered here in multi-resource case with 6 front halls, 3 back halls and 1 cloud computing resource. Consider we have two slices with each contains 3 classes, that is class 1, 2 and 3 belong to slice 1, class 4, 5 and 6 belong to slice 2, and their corresponding demand vectors with mean workloads and arrival rates are specified here. The performance trade-offs for this setting is observed here as shown in these two graphs, the rate trade-off and delay trade-off. In the rate trade-off, it is clearly observed that SCS and DRF outperform DPS in the mean throughput, and similarly for delay trade-off we have three curves showing almost similar delay. Now concluding the discussion on this paper, the proposed SES in this paper allowed good resource allocation with interest protection, load-driven elasticity, and also desirable good performance at the same time. In the future, this approach can be extended as, for example, if slices have highly imbalanced spatial user distributions, it may be useful to let the slices itself specify different shares across different pools of resources it needed, and if slices may wish to request different shares across types of resources may also be possible. Thank you.